Thanks everyone for coming today and welcome. So my name is Doug Ray. I'm going to be the moderator. I believe any questions that come up, feel free to just ask. Don't worry about waiting till the end of the talk. But yeah, I know it's great to see a lot of new faces as well as some familiar faces. It's, I'm sure the past couple of years haven't been easy for a lot of people, but it's great to be back here. So for folks who are new to DataWorks, I'm sure you're going to really enjoy it. I'm proud to introduce today Victoria and John. They work in the Systems Analysis Division, my division in our organization at Picatinny Arsenal. So we work in the Systems Engineering Directorate in the U.S. Army Combat Capabilities Development Command. All new names, new acronyms, but yeah, so we work at the Armaments Center. Victoria is an operations research analyst and direct fire team lead. Her experience lies in machine learning, data analysis, modeling, and simulation, and she's been working in the division since 2018. She has earned her BS and MS from the College of William and Mary. John is a computer scientist in our division. His roles and responsibilities include developing interactive dashboard visualizations, researching innovative AI, ML capabilities and technologies, and conducting trade studies. He holds a bachelor's in computer science with a minor in mathematical statistics from East Stroudsburg University in Pennsylvania. All right, without further ado.
Thanks, Doug. So we'll get started. I'm Victoria. That was obvious, I guess. So instead of doing PowerPoints, we decided to use Jupyter Notebooks. All of the course material was uploaded. If you don't have the ability to use Jupyter Notebooks, we also uploaded them as PDF files. The only thing the PDFs are missing is some of the GIFs that we included, but everything else is there. So for this first notebook, it's pretty much just the agenda of what we plan to cover today. So we have a nice XKCD comic. And so basically what this mini tutorial will be covering is data integrity for deep learning models. Do you mind making this tiny, John?
Yeah.
Thanks. So here's the course abstract. One of our coworkers was going to be leading this course, but I guess about 6 weeks ago or so, we found out that he would no longer be able to lead it. So John and I kind of picked it up and ran forward with it. We decided to lean more in on the data quality instead of data integrity, but we kind of do cover data integrity a little bit and what those differences are. So if you have any questions after the fact, we have our emails if you want to reach out to either of us. And the first section will cover what learning means for statistical models. Then we'll get into a short review on deep learning theory and neural networks. The last section of content will focus on, or theoretical content will focus on data quality. And then John will go over a practical example with an Airbnb data set. We did really want to have something that was a bit more applicable to us, but we kind of had struggles finding something that was distro A that we could work with given the time frame, so we decided to pull something from Kaggle instead. So for this first section, we're going to cover what does learning mean for statistical models. So when we're talking about a hypothesis space throughout this course, we're kind of referring to a candidate model that approximates the target function. So that target function could take the form of y equals mx plus b. Could also take the form of y equals ax squared plus bx plus c. They're all different examples of types of hypothesis spaces or candidate models for our data where maybe we know that it wants to be in some type of form or regression form like this, and we're trying to estimate what those parameter values should be. So these are all examples of a hypothesis space of linear models. It's kind of an example here where all of these blue dots represent the data points, and then we have a few estimated functions to try and fit to that data. And when we're doing deep learning, there are a lot of different hypothesis spaces like decision trees or artificial neural networks, and depending on the data, when you kind of decide on a class of models or what that hypothesis space should be defined as, the next step is then kind of finding the ideal model within that hypothesis space. So maybe we know we want to fit some type of linear model, but we don't know exactly what kind of linear model. And all of that is all of that is part of the learning process for machine learning. So moving on to loss and objective functions. The loss and objective functions is how the model does learn to the data. So the loss of the model is a measure of how well it compares to the desired output. So for here, it's just a sum of the loss over all points within the data set. And whatever that loss or objective function is going to be, that's going to depend on the hypothesis space and what your goal is with the data. So it could be mean squared error, mean absolute error. I'll get into a few of different types of loss functions. But depending on that hypothesis space, it's going to kind of determine or narrow your field of possible loss functions. So here we have just one GIF for a regression model where on these two axes on the bottom, we have beta 1 and beta 0. So that would just be the intercept and the slope. And then that y-axis is the MSE. And so this surface kind of represents all possible regression models within these beta 1 and beta 2 values. And I don't know if you can see this little dot as it rotates around, but that's where the MSE is minimized. So that would be the model that you would want to move forward with if you wanted to minimize MSE. So this is kind of just a visualization of what the loss looks like over that space of possible models. Here's another example, but instead of MSE, it's the maximum likelihood estimation. So this would be for some type of classification model where we're trying to fit a curve to our data and see which model is most likely going to result in the data inputs that we have. So what values of loss do we favor? That, as I said before, is going to depend on the hypothesis space. So whether it's MSE or cross-entropy loss, maximum likelihood estimation, that's going to kind of be determined by the problem that you're trying to solve. Now, when John and I were putting this together, we were talking about the difference between loss versus accuracy, because with each iteration of learning, the model is adjusting its parameters based on the loss. But at the end of the day, when we're trying to deploy the model, what a lot of decision makers are really concerned about is actually how accurate it is. So we made up this little graphic here of that relationship between loss and accuracy, where loss is the measure of how well our model behaves after each iteration of optimization, and it's the distance between true values and predicted values, where accuracy is used to measure model performance in some type of interpretable way. So here's a little plot here with the relationship between low accuracy and high accuracy, and low loss and high loss. So low loss, low accuracy, that would mean small errors on a lot of the data. High loss, low accuracy would be large errors on a lot of the data. High accuracy is small errors on only a few of the data points, and then large errors on a few of the data points. So this is often also represented as kind of those target practice plots, those archery targets, but here's just kind of another way to think about it. So based on values for that loss function after each iteration of the model is when the model is actually learning. So learning is the model is trying to optimize to a specific objective function, which is the loss function, whatever function that may be. So if it's trying to minimize MSE, it's going to adjust the parameters until that MSE is as minimal a value that it is able to find. So here's two more GIFs kind of representing that, where we have this surface of possible regression functions, and each red point is an iteration in learning. So you can see it kind of starts to take big steps, and then as it gets closer to the minimum, it kind of narrows in and makes smaller and smaller changes as it kind of tunes into what that minimum value should be. And as a representation of what that regression function might look like, we kind of have that over here where the slope is like drastically changing, and then the intercept and the slope kind of starts changing a little bit less as it fits a little more finely to whatever that data set is. So when we're learning, we're adjusting parameters and kind of trying to zero in on where those minimum objective values will be. Here's one more GIF showing pretty much the same thing. Instead of a 3D gradient descent, it's just a 2D, but you can see it's looking at the derivative of each step and trying to see where that derivative slope of the loss function is going to be equal to 0. So kind of taking a step back, I suppose, when we talk about learning. This is stuff that I know we all already know, but I think it's important to keep in mind. I read a really interesting paper about this, and I decided to include it in here. So machine learning models are really just complex math equations. Yeah, they are inspired by brain neurons, but we all know that's kind of a stretch. And recently, language about machine learning is really anthropomorphic and uses these ideas of human intelligence when talking about them, when it's really, a lot of the times, just complex matrix multiplication or some other types of functions. So there's two quotes down here, one for IBM Watson and one for AlphaGo, which is IBM Watson machine learning model. AlphaGo is a machine learning model made to play the game Go. And here this first one says, "Hello, my name is Watson. I'm a cognitive system who can understand, reason, and learn." And then this other one says that AlphaGo had thoughts about how well it was going to do. And this is really common for colloquial vocabulary about machine learning, but I think it's important to keep in mind, not only when you are talking with people in the public who maybe do not know anything about machine learning, but also leadership and decision makers, and even for ourselves when we are building these models. I think it could subconsciously or unintentionally influence the way that we think about these models that we're building. So I don't have any solution. I can't think of a better way to talk about these models, but I think it's important to recognize that these models aren't learning common sense. They're just picking up on patterns and bias within the data to try and minimize whatever your objective function might be. Can you scroll down a little bit?
And feel free to ask questions or interrupt at any time. I know Doug said that before, but just reiterating that.
So I feel like that part of all that anthropomorphicness of machine learning models, it kind of leads into the motivation for this course for data quality and machine learning, because models aren't learning stuff that humans might be able to recognize in the blink of an eye. It's only learning what is there in the data set, which is also known as narrow AI, which is what most of us are used to working with. The models only know the scope that we give it. General AI is kind of sci-fi in the future, and some type of model that or AI architecture that can understand or learn any task that any human can, no matter what the discipline is. Obviously, that's not what we're talking about here. So in terms of a model only being able to know, there I go again, the scope of the data that you are providing it, if you're not providing it with quality data, you're not going to have a quality model. And because machine learning so relies on volumes of data to be able to learn, they're kind of, like, data quality and machine learning, I feel, are really inseparable and kind of intertwined topics that need to be considered together. So if you have bias within your data, the machine learning model is going to learn that and respond to that. And it can lead to unintended consequences. It can even lead to catastrophic consequences. One example of that, or one symptom of that, is shortcut learning, where your model may perform really well on the test set, but for the wrong reasons. And so if you could scroll down to show this full image, John, we have this data set of stoplights. We are trying to build a model that will be able to identify whether the light is red or green. And this small sampling of images is representative of the full data set that we have. Do you guys see any, this is a discussion now, looking for feedback. Do you guys see any issues with this data set?
If the pattern continues, I think the pictures with buildings behind the light have green lights.
Exactly. All the red lights have sky behind them, and all the green lights are in some type of city or building landscape. So on our test data set, our model might perform really well at predicting what lights are green, but then when we actually go to use it in the real world, we find that it doesn't work too well because it didn't actually learn or pick up on patterns about like maybe the position of the light to see if it was red or green, but was actually picking up on whatever was in the background. So these are kind of things that you need to consider and think about and look into your data set when you are trying to build a model. So you could click on that if you want. So we kind of just covered that. And then it looks like one of my images didn't load here, but that's okay. I did have one case study here. Says one algorithm may not fit all, how selection bias affects machine learning performance. So this paper is really interesting. It was mainly focused on medical applications, and the gist of it is that medical machine learning models perform really well and even outperform radiologists on test data, but when they are actually deployed on real patients that maybe were not part of a study, they do not perform very well. And that's because due to selection bias in the participants that were included in those training and test data sets versus the general population of patients that it was finally deployed upon.
What was different about those two sets of patients?
So this paper looked at a few different cases. It wasn't just one sample or like one machine learning model, but what it seemed like, and which I have seen with actually some dermatology stuff as well, is that when they're trying to build these models or when they're capturing data, it seems like whatever condition they're trying to find, it generally has a higher incidence of that condition is included in the data set of patients that have that. Yeah. So this is pretty much the end of the first notebook. There's one more XKCD comic. The first guy says, check it out. I made a fully automated data pipeline that collects and processes all the information we need. And then the woman says, is it a giant house of cards built from random scripts that all completely collapse the moment any input does anything weird? It might not be. I guess that's something. Whoops, just collapsed. Hang on, I can patch it. So I also included some recommended reading. This is where I pulled a lot of that anthropomorphic colloquialism that I talked about above. And then I have a few extra tips of learning. They pretty much all show, this first one is K-means clustering, learning a decision boundary. They kind of all show what those first GIFs that I showed, they kind of depict the same ideas, but I didn't want to cut them because I think they're really cool. So that's the end of this notebook. The next notebook is going to be a refresher on neural network architecture.
Question. So you don't have to get to this right now, but I'm wondering in terms of like data quality and data integrity, so I have programs where they go to new environments and it just breaks, right? And the question is, they always have is, well, how much data is enough, right? And so are you going to kind of speak to about how I can get to that knee in the curve for my data sets in terms of, like I have systems that work for the US Navy that need to operate in any water in the world, right? I can't test everywhere as much as I would love to, but so
Yeah.
what do I need to do to ensure that, when I give this to a sailor, it doesn't blow up in their face?
I think that's a really difficult question.
I think that goes kind of into my example I talk about later and stuff. I just have data just in New York City, but that we only have so many Airbnbs in New York City. If you want more data, we need to go to a different city, but then the scope of the problem changes then. So what do we do? Do we go to different years and then scale the currency based on inflation? Like, and what other factors can we pull in? So that's a very loaded question and stuff that, yeah.
And I think
But it's definitely a very important question, definitely too, because you do need massive amounts of data for these types of models.
And I think that also goes into what the keynote talk that we had today, where that data literacy needs to be taught and understood at all levels of leadership, because yeah, we are the SMEs for data analysis, but I think the question that you're trying to answer, it kind of depends on the problem, and it needs SMEs from whatever that application is to try and bound the problem. But if they don't know anything about this, they're not going to really have any input as well. I think there is a knee in the curve somewhere, but I don't know if I can answer where that might be.
Sounds like it might also be related to the general versus narrow AI.
Yeah.
Whereas you might need a type of algorithm that might not exist yet for more general learning to be able to perform on things that we can't train it on.
And I think I forget the name of the NASA woman, but she also talked about digital twins. And I think those digital twins could be helpful if you can't get the actual data. Maybe you can simulate some data. Obviously, that's a much bigger problem than the one sentence that I just said it in, but that's also an avenue.
Kind of makes me think of, I was in the categorical data analysis short course yesterday, and something that came up that's always been an issue in that field, and I know very little about it, but survey sampling, I don't know if there's there's been research done to kind of integrate those methods, stratified sampling from surveys with AI kinds of problems. Something to think about. I don't know.
For sure.
Can I hop onto that? So
Yeah.
I think that's exactly right. So I come from a statistics background too, and I think the main problem we see is we just assume that the data we get will apply to generalize to any future scenario. And of course, there's problems with that, but it's not the algorithm, right, that's biased. It's the way the data was collected. So
Right.
it's like there's two different directions, at least two directions you could take. One is understanding the population of the data you have and understanding that applies to that, or devising sampling strategies to collect the data that you will actually need in operation. And I think that's the part that everyone just takes for granted. They just say, oh, well, this is the data we have, it's good. And it's definitely not true. And I think, yeah, now we're seeing that.
Yeah.
Good discussion. So moving on, this notebook is going to focus on an overview of neural networks. I'm going to assume that some of you are familiar with this, some of you may not. I'm going to think there's some type of varying experience with neural networks, so I'm just going to give a brief overview. And if you have any questions along the way, feel free to ask. So just going over some common buzzwords. We've got artificial intelligence, machine learning, data science, deep learning, and artificial neural networks. So and if could you scroll down just a little bit so that the Venn diagram? Yep, thanks. So here we've got artificial intelligence. It's kind of the big bubble, and is the study of agents that perceive the world around them, form plans, and then make decisions to achieve their goals. Machine learning is within artificial intelligence because it does do that, but it does it based purely on observed data. So if you wanted to build a model that could play Sudoku or tic-tac-toe, it doesn't necessarily need to have any observed data. You could just give it a set of logical rules and to make decisions and learn how to play the game. Deep learning is then a subset of machine learning, where it's focusing more on artificial neural network models like convolutional neural networks, residual neural networks, or even just plain vanilla neural networks. And then data science kind of overlaps all three of those bubbles, focusing on extracting knowledge and insights from the data. It can include any of these types of techniques, but it doesn't necessarily have to. So moving on, just a quick section here. I threw in a few links. I'm not going to click on them today, but just some examples of AI and machine learning in the Army, kind of as a motivation of why is this important to us in the defense industry. So there's some predictive maintenance, threat detection, things like that. So if you want to click those links, read those articles in your own time, they're there. Those links are there for you. Moving on to neural networks basics. The underlying structure is called a perceptron, which is, you can think of as a compute node or a perceptron. We have a set of inputs, x1, x2, and x3, and each connection into that node has some type of weight, w1, w2, w3, attached to it. Those inputs all get multiplied by the weights. A bias is added, which is not visualized here, and then within this node, there's an activation function which transforms that sum into a y output. So one single perceptron is a single layer neural network. The plain vanilla neural networks that we all know and love is made up of layers of these perceptions and compute nodes. So these neural networks are unlikely to hone in on human constructs. If we were using it to, say, predict like the MNIST data set, those handwritten digits, we wouldn't be able to point to one node and say, oh, this one is picking up on like those double O's of an 8. It wouldn't pick up on things that we as humans are able to easily interpret, which is why it's called a black box model. But it can also handle nonlinear relationships and other complex relationships. So that's kind of the main benefit and strengths of using these types of models. So if you're trying to remember what happens at each node, just remember inputs times weights, add, bias, and activate. I'll probably say that like 5 times today, but just remember 2 things are happening at each node. We're summing the inputs times the weights and the bias, and then it's going to go through the activation function g of x to get that y value. So if we're looking at a few examples of neural networks down here, the compute nodes or the perceptrons are all organized in layers where outputs from one layer feed in to the next layer. During a forward pass, there are no cycles allowed, so information that starts here is only going to be moving forward towards the output layer. It's not going to move backwards during forward propagation. In addition, all nodes from one layer are fully connected with nodes in the next layer. They're fully pairwise connected, but within one layer, no nodes are connected. So this kind of just goes over a little bit of terminology. When we're saying in n-layer neural network, we don't count the input layer. So this one on the left is a 2-layer neural network, and this one on the right is a 3-layer neural network. So in terms of sizing, we can see this 2-layer neural network. If we add up all of the parameters, we've got these 6 neurons, 20 weights, which is the number of connections, and then 6 biases, because there's one added bias for each node. So that gives us 26 learnable parameters. And even modern convolutional neural networks can contain hundreds of millions of parameters if you really stack up those layers. So we can already see here, if we're thinking about comparing this to a regression model, this only has 2 layers in it, and we've got a ton of learnable parameters, which really is the strength of these neural networks to try and fit to complex data sets and pick up on those underlying relationships within the data. So I'm going to kind of move forward in a cycle. I'll start with forward propagation, then I'll cover activation functions, loss functions, and then back propagation, just as kind of an overview of what a turn of the crank looks like in an iteration of a machine learning model trying to learn. So forward propagation is the calculation and storage of intermediate variables and outputs all the way from the input layer to the output layer. So it really is repeated matrix multiplication interspersed with those activation functions at each node. So you really could do this by hand if you wanted to. Yes, it would be tedious, but it's easy to understand. It's just a lot of matrix multiplication again. So what do these weights represent? Oh, could you actually show that little thing again? Yeah, thanks. So what do weights represent within a model? They represent the amount of influence that an input has on an output. You could think of it as the strength of connection between units, but again, it's not something that is human interpretable. And before the first pass, weights do need to be initialized. So they could be randomly initialized. Again, with each step of back propagation where the model is adjusting those parameters, they will, with each epoch, nudge those parameters one direction or another to minimize the loss or objective function. So whatever weights you initialize as, it doesn't matter. They can be totally random, but they can't just start at 0. So can we determine what these hidden neurons represent or what the weights represent? No, but that's okay because we don't need to. Again, it's kind of you can think of it as like a black box. It's unlikely to hone in on human constructs, and you can't really confirm that it did if it did. I think this is probably a big challenge with talking to leadership when they start asking questions about exactly what the model is picking up on, but I think that's kind of our duty to present the output and results in some type of interpretable way to kind of break through the fog of what the model is doing, even if we can't say that this weight value of XXX represents YYY. So moving on to bias, I will cover this a bit later, but bias is a learnable parameter, and it allows us to kind of shift the origin of the activation function. So when we're trying to determine the number of layers and sizes in our neural network, generally the more layers you add, the more complex the model is, the more complex relationships the model is able to learn. So here's a small red-green classification where we have 3 hidden neurons, 6 hidden neurons, and then 20 hidden neurons. The risk that you take with having a highly complex model is that it could overfit to the data, which it seems from this graphic that it is. That can be mitigated with regularization or some other types of mitigation techniques. But generally, as you increase the size of your network, it will be able to learn some more complex relationships. If you don't have enough neurons, you risk underfitting to your data. So the next step is training a model. So like I said, we start at forward propagation, which includes inputs times weights, add bias, and activate. The next step is calculating the loss function. So whatever the objective function may be, MSE, MAE, cross entropy loss, we see what that value of loss is, and then we back propagate. So we move backwards, starting at the end of the network. If you can imagine, the outputs are over here, the inputs are on the left. We start to move backwards and kind of nudge those weights and the learnable parameters to try and get a lower loss value the next time we forward propagate. So moving forward into activation functions. Activation functions happen after we input times weights and add bias. The next part is the activation function. So generally, we want them to be differentiable because the derivative is needed for back propagation. And here I will list a few activation function options. I'm not planning on going in depth, but I do have some information here, so it could be used as a reference. This is kind of more of just an overview again. So the first one is the sigmoid. This is that S curve it basically squishes all inputs into values between 0 and 1. It is represented by the blue line. The red dotted line is what its derivative looks like. And advantages of this is that it's differentiable and all of the output values are between 0 and 1, so it kind of keeps your problem within, or your inputs within that range. It does have some disadvantages though. If you could scroll a bit, John, which is that vanishing gradient problem. So that derivative value at the ends, it really starts to converge towards 0, and when the derivative is 0, during back propagation, it could effectively kind of kill that gradient and have almost no signal flowing through the neuron to the next layer, which causes slow convergence. So Sigmoid used to be really popular. There are a few other activation functions that have since become more popular, pretty much because of the vanishing gradient problem. So one example of that is TAN-H. It still does have the vanishing gradient problem, but generally does perform better than the sigmoid. You can see instead of between 0 and 1, it's between -1 and 1. Moving on to the next one, we've got Relu, rectified linear units. So with this activation function, anything less than 0 will be 0, and anything greater than 0 will just be whatever that input times weights plus bias will be. So this has recently become very popular. It's very computationally efficient. If you could scroll down a bit, John. And it generally has improved performance compared to sigmoid and TAN-H. Some disadvantages are the dying Relu problem. So if the inputs approach 0 or are negative, then the gradient just becomes 0 and the neural network won't be learning on that node anymore. But there are a few, I guess, flavors of Relu that attempt to fix this problem. One example is leaky Relu. So there's like a very small slope of 0.1x to try and keep that update alive. This has become very popular. There's also parametric Relu, and I think I have another one listed as well, and exponential Relu. One last activation function is max out, which just takes the max of the inputs. So here we have like, oh, if you go up just a tiny bit, max of weight 1x plus beta 1, weight max of, or weight 2x plus beta 2, or all of the nodes that are feeding into that perceptron. So moving on, those are activation functions. So that basically transforms your node, all of the inputs, into the output that will either be the output of the model or the output that is feeding into the next layer of the neural network. I also have softmax as well. So once forward propagation is done and activation functions for all layers have been computed, at the end we will either have one continuous value, or if it's a classification problem, we might have probabilities, or maybe just a 0, 1. And at this step, this is when we're going to calculate the values of loss. So neural networks use loss functions to calculate model error, and back propagation, which occurs after calculating the loss value, will be trying to minimize this loss. So there are a lot of options. Again, it depends on your problem space. So for regression, i.e. for continuous output values, again, I have a few listed here. Probably not going to go in depth with them, just kind of wanted to show that there are options. We've got mean squared error, mean absolute error, Huber loss. There are a lot of other ones that I don't have listed here. I will say that TensorFlow and scikit-learn have almost all of these, well, definitely all of these, plus a lot of other ones implemented. So you do not have to implement it yourself if you're using Python. I'm not totally sure what coding languages you are all familiar with, but John and I mainly use Python for machine learning. And then for classification, where outputs should be between 0 and 1, we've got cross entropy loss, and then a few multi-class options as well, like hinge loss and KL divergence. So the next step in that cycle of forward propagation, loss, back propagation, we're up to back propagation. So I've explained this, I think, successfully twice before, so let's see if I can do it clearly again for a third time. So once the loss is computed, here's kind of an example of a neural network. Looks like we have 4 outputs here. We're going to move back through the network and adjust the weights. And those weights are going, or I guess first, the gradient of the loss function with respect to the weights will be computed, and the weights will be nudged in a direction in an amount that is proportionate to the effect that it has on the loss function. So this is something you could implement yourself. It is like a really tedious application of the chain rule, essentially. But it is also implemented in TensorFlow. So if you don't have to implement it yourself, I would not recommend doing that. If you could scroll a bit, John. After feeding forward through the network, an output is moved back through the neuron, slightly adjusting the weights to drive the cost down, and each weight in the network is nudged in proportion to how much it contributes to the overall error. So if this is happening iteratively after each epoch, and it uses memoization as well. That's not a typo. What memoization is it stores previously computed results to avoid recalculating the same value. So it's not going to be kind of stuck in this loop of doing the same thing over and over again. One thing to keep in mind with backpropagation, which I touched on briefly above, is the vanishing gradient problem. So particularly for sigmoid and tanh, that derivative converges to 0 at the tails. And because backpropagation uses the gradient to train the weights, if the gradient gets down to those very small values, it makes it difficult for the model to train. So I would recommend probably using a different activation function such as Relu or leaky Relu. So yeah, this was the neural network overview. I think if there are no questions at this time, yeah.
So I've actually always had a problem trying to understand the vanishing gradient problem. I think I understand each of the bullet points. I think I just lack the simple intuition to kind of put them all together. Could you, if you don't mind, could you kind of talk a little bit more about how the activation function actually leads to the vanishing gradient function?
Sure. Would you mind going up a bit, John? I'll tell you when to stop. Stop. Okay, so let's say we are looking at this plot here. Let's say we have like inputs 1, 2, 3 and weights A, B, C. So that sum will just be like A1 plus B2 plus C3 plus B for the bias. And we'll get that sum. Let's say that sum is X. And then that function will be put into g of x, which is the sigmoid. So then if it's the sigmoid function, that value is going to be between 0 and 1. So that's the forward propagation. I think you're all good on that part, right? So if we want to move, let's say now we move through the network, our loss is calculated, and we want to now back propagate. So we've got this network, we have all of these different weights, and we want to calculate the derivative of the sigmoid function, which is gonna, I wish there was a whiteboard mark here, that's okay though. The derivative of the sigmoid function, which is that little heap there, we'll see how much each of these weights kind of contributes to that loss function, which let's say it's, I don't know, MSE. So I think I want to start my sentence over again. I did, okay.
I can pull up Paint if you want to like just draw.
No,
Okay.
that's okay. But man, I did this work so well one time, and I've never been able to replicate it.
Sorry, I asked that question.
No, that's okay. So when we actually, could you go over to maybe the course one?
The derivative of.
Just like a GIF of gradient descent, I think might be helpful. This is good. Down a little bit. So this is kind of a simplification of gradient descent. There's only really just the cost and then the parameter. When in neural networks we have multiple parameters that are kind of feeding into that sigmoid function. But you can see that the gradient descent, if this were to be the derivative of the sigmoid function, which it's not, the function is looking to see where that derivative is equal to 0. And when we are at those tails, the derivative is so small. Oh, okay. I think I've connected a few brain neurons. But when we're training, if the derivative is large, we're going to be taking larger steps, right? It's like when you're running down a hill, when it's really steep, you're moving forward a lot faster. And then when you start to get to that valley, you're going to slow down and take smaller steps until you're at the minimum. And it's kind of a similar concept with the gradient descent of sigmoid. When that derivative is larger, like we're going to try and take larger steps to try and get to where the minimum is. However, when the derivative kind of narrows out towards 0, we're not going to be taking any steps anymore. And so the model is not going to continue to learn like it would. I guess I wouldn't think of it as like a local minimum, but if you wanted an analogy, you could think of it as like getting stuck in a local minimum.
I don't know if it impacts this, but what I've seen other problems is that look like round off errors kill me. Or if the gradient got to be too small, round off errors made it go away altogether. So then you would think it ought to be converging just really, really slowly, but in fact it didn't seem to converge at all. So that could be something that goes on here.
Definitely.
So I think the way it works, and it's been a long time, so I think it's the update step, the update gradient for the weights, right? That's what you're trying to solve for. I think it's proportional, and if you do the math, it's proportional to the gradient, to the derivative of the activation function, right? So if you are in a part of the activation function where you're at 0, it doesn't really matter, right? 0 times anything 0, so that you get stuck.
Was this helpful?
You have no reason to like move beyond because
Exactly. Yeah.
there's no cue that tells you I gotta do something else. It's a kind of intuition.
Where the activation function is flat, you can't tell if does changing the parameter, how does it move me on the activation function? The math says it's not making any difference no matter which way I move, so I'm not moving.
I think I can just add, I think this is more of an issue for deeper networks, because the problem is that when you do the back propagation, if you have, so imagine like you're trying to train the whole network, and let's say you kind of reach a local minimum in terms of the weights for the last layer, and those gradients go to 0. And now since you're kind of using the chain rule and multiplying these through, you can no longer learn on previous layers.
Nothing's coming from nothing.
Right, so it becomes 0 the whole way through. And I think that's the, as far as I understand it, that's sort of the main issue actually.
Yep.
If you only have one layer, then you've probably just hit the minimum. But if you have
Yeah.
multiple layers, you have a problem.
Yep, that was a really good point to bring up as well.
Can I ask a question? You made a comment about not being able to learn what these neurons, what these weights mean. But there are tools, right? There are methodologies to kind of like visualize the activations in terms of the input.
Yeah.
And so I guess my question is there ever a point, is that enough for us to trust these models? Or because let's say I'm a pilot, right? I'm not going to give weapon release consent to an AI. I don't know exactly what it's doing, right? And if I have an architecture which is a black box, I'm never going to hit I trust you, right? So is that I mean, are we going to use these things in that way, or is it there's always going to be very, very niche until we develop a way to figure out what's going on?
I think it's probably going to depend on the application. So like I still can't remember her name, the NASA keynote speaker said today, these aren't replacing human in the loop. Like the human in the loop, I think needs to remain the human in the loop, but they can help maybe augment the decision. And depending on that, what that decision is going to be, I think is going to kind of dictate whether AI and machine learning can replace or to what extent they can augment that decision. Like if it's shoot, no shoot, it shouldn't be replacing that ever, I don't think. If it's something like predictive maintenance, I think there's probably a larger area where machine learning can kind of step up a bit more in terms of that. In terms of understanding the model though, I think that this is a growing field. It's growing really rapidly. I think more tools will be developed. And I think that as time goes on, we probably will be able to pick up on more insights on what the model is picking up on. But we do also, without those visualizations, we run the risk of that shortcut learning, right? Where our model is learning to predict if it's a red or green light based on if there are buildings or not, instead of what the position of that stoplight is in. So that bias within the data, that data quality, if you don't have great data quality, I don't think the machine learning model should be trusted. And in terms of determining, is your data quality, or is it good quality data, that can be a difficult question. It kind of needs to happen at several stages throughout the machine learning process, and it does need to be examined or re-examined frequently, even after it is deployed. I don't know if I gave a great answer to your question, besides if I were to sum it up into just a few words, I would say maybe, but not right now, or like it's possible.
It's really a question about neural networks, right?
Yeah.
Because, these things tend to be black boxes, especially since the contractor won't give me any data, right? So I just trust me, it works. Okay, right? And I tested it in 2 places in the world. That's enough, right? So you can imagine that there are other models which are more explainable, right? You can, we've done things like, decision trees. I understand what a decision tree does, right? I can go through that and it can be autonomous. So I guess the question is this just because why are we so focused on neural networks now? Is it just because they're in vogue? Because we have K20s, GPUs that can do this. Because I have trouble seeing how we're ever going to get to a point where we trust these things to do the things we say we want AI to do.
Mm-hmm. So I don't know if you had something that you wanted to say, but we're over the last several decades, we've gone through AI winters, and I think they're either called AI springs or AI summers. And right now we're definitely in an AI summer. Like there's a lot of funding, a lot of resources. We're really trying to expand our capability, and there's a lot of focus on these right now. And generally what happens is we realize that the problem is still a bit out of reach, whatever that problem may be, and then it kind of leads to an AI winter where they become less popular, they fall out of favor. In terms of why neural networks, especially right now, I think we have a lot of data, and we've had a lot of data for a long time, but I think right now we're in this unique time where a lot of that data is finally becoming usable and can be leveraged in a way that it wasn't before, partially because of that GPU and expansive computational capability, where maybe our other models weren't really built or able to use such a large amount of data that these neural networks can. And also picking up on some other complex relationships within the data, like image classification, for example.
So he asked me if I have access to the model for the things I'm working on. Nope. Right? It's because that is how the contractor makes their money, right? That's they're never going to give me that.
Yeah.
Right. And so I will, unless we get better lawyers, I'm never going to see I'm never going to have purview into either the data integrity or the model integrity. Right. So what am I supposed to do other than go, I'm going to try to break you during tests, and that's all that I can do. That's my one simple check.
So I don't know if this is something that, certainly something that's easy to do with neural networks and gives you a little bit more insight into activation functions and how the layers are working is you can do what's called, and I mean, this should be easy enough to ask them because it's super easy to do is just drop out. So you randomly turn off
Yeah.
a whole bunch of different neurons throughout, and then you get sort of an ensemble of different models. And you can tell, do all these neurons work? Are they meaningful? If you have this large, error within a dropout, you can essentially say like, there's one neuron that's doing a lot of work for this. That probably means that this model's not particularly comprehensive. So I don't know if that's something that you could do, but I mean, it should be.
Like you just have inputs and outputs.
Yeah, so I can't even get, so like, but they won't even tell us how they're doing the feature engineering, right? Because, remember, right, most of these places, this is their product, right? This is their secret sauce that they're using to get money from the government, and rightfully so, but they're not going to give it to me as a tester. And they're not going to give it to the government either, right? It's not part of the contract deliverable. And so we're stuck in this place where I can't do anything about it other than try to find places to break you.
Mm-hmm.
And even if I don't break you, that's not assurance. That's just saying I couldn't find it in this under my very limited TME budget. So I have a beef to grind with neural nets. So.
This is a general machine learning question, not necessarily neural network related, because you have this problem regardless of the kind of model you want to use. But I mean, there's other techniques like cross validation. There's a whole
sure,
it's not
sure.
just the neural network thing.
My only point about the neural nets is that they tend to be black boxes, right? That's how they get sold to us, right? Whereas other things, if I do a regression, I can understand a regression. Right? I can understand, K-means clustering. I can understand, I can put human intuition to those things. I can't do that for these.
I think a lot of it also depends on how you're defining your inputs, because it could be something that a person recognizes, like distance or something, or it could be like Fourier transform vibration data from the sensor. So you have I think it really depends on how you define the inputs as well.
Are they not comparing the performance or a linear regression, for instance? So that should be I would say at the most basic, you should compare any deep learning, machine learning model to a simple model. If you're beating linear regression by 0.5% accuracy, first of all, if that's important, okay, that's fine. But if in your context, your problem, 0.5% or whatever doesn't matter, you should probably be using linear regression, right? Because like you said, you know what it means. You know what it does under the hood. You know how it would extrapolate in new space.
No, I agree. The problem we're running into, right, is so I support OT, the operation testing. The problem is we have a system that isn't working, and we don't know, is it the data provenance? Is it the sensor? Is it the learning? Is it how they're training? Because all of that is opaque, right? And it's made more opaque because the model is a black box. So it's like, okay, well, all I can do is try to train you someplace, put you someplace new and see what happens.
Yeah. I think what you said brought up is it's a very real point that I think neural networks, like Victoria just said, it's like in this summer where everyone is saying they just want this. They want a deep learning model or whatever. They're just saying that because that's what everyone else wants. But really they want a model that gives them a solution or the best solution for their problem. And that's not, I don't think, always going to be a neural network, but that's how I guess you get.
So this notebook is going to focus on pretty much just on data quality. So, and then the last notebook will be the example. So what is the difference between data integrity and data quality? Data integrity is in the title, data quality is not. There's a little more than that. So they both do deal with the condition in the data, but in different ways. So data quality is, I kind of think of it as more zoomed in to the actual data set. It has to do with completeness, uniqueness, validity, timeliness, consistency. Is this data reliable? I find that it's easy to overestimate the quality of your data and underestimate the consequences of poor quality data, but it is really important to try not to do that because poor quality data can be catastrophic. Now, what is data integrity? I feel like this really tied well into the keynote this morning where data is an asset. So data integrity does encompass data quality, but also deals with things like data integrity, data enrichment, data governance, location intelligence, sharing data across different resources. It seems to be a bit of a more like enterprise or organizational-wide concerns and conversations, trying to avoid things like data silos, where a collection of data is held by one group but is not easily or fully accessible by other groups that may need access to it. So I'm pretty much just going to be focusing on data quality, but I did want to at least touch on data integrity just to kind of fill in that background. So why is data quality so important? I am repeating this fact, but because machine learning relies on having volumes of data to learn, the two really are inseparable. And when you discuss one, you should be at least considering or also discussing the other one. The quality of the data that we train on is going to affect how well our model is able to generalize when deployed or looking at new data. So having strong data quality is an opportunity to develop an effective machine learning model for whatever your problem or application may be. And once that model is trained and deployed, it's going to be indifferent to bad data. It's going to continue to make predictions. In this case would be bad predictions regardless of data quality. And when I say bad data, I'm kind of referring to data that falls into some of the data quality issues that I will cover in section 2. But I don't want to go there just yet.
Got you.
So one issue is data drift. So differences in the training data versus production data or the population data. So this kind of has to do with that case study that I mentioned before, where maybe the selection, you could think of it as that selection bias in the medical machine learning application, where maybe the population that was included in the training model for some feature, maybe it's incidences of some type of condition, had a distribution that looked like this, but when it was finally deployed in 2021, that data distribution kind of changed and was a little bit different. So this leads to model accuracy kind of degrading over time, and I kind of like to think of it as being something that can be silent but deadly to your model performance. So moving into distinct data quality issues, the things that we really are concerned about. We've got completeness. Is our data missing any data? Is it missing columns or rows that should be there? Is it consistent? Are there any contradictions? Is it accurate, unique, current? Are there any outliers? What should we do about them? Are there any biases within the data? Often this shows up in the media as gender or race biases, but it doesn't have to be, particularly within our field of defense. Cursive dimensionality, and then feature selection and extraction. So at this point in time, I would like to discuss a few of the projects that I've worked on, just to touch briefly on how they kind of tie into some of these data quality issues. So if you could stay on this for a minute, John. One project I worked on was an image classification problem for UAS in infrared data. And this project was kind of a COVID stay-at-home project. It wasn't guiding any decision makers or leadership, but it was kind of a proof of concept of, can we do this? And that data, that infrared data, it either had a UAS in it or it had clouds. It didn't have birds or trees or any type of object in the sky. And when I wrote up my report on it, I kind of made a note that, yeah, these are the images that I have, but I don't know if there might be other things in the sky if this were to be deployed that could affect how accurate that model is. So in that case, because I knew it was kind of just a proof of concept and it wasn't actually being deployed or guiding any decisions, I made a note of biases that I noticed within the data, but I didn't take any actions such as expanding my data set. If it were a more high priority project, I probably would have done so. So for a project that I'm currently on, we are again doing image classification, but instead we've got manufacturing data, and we're trying to identify manufacturing defects within those images of munitions. And there are some issues with the data set, and we're not totally sure. They're kind of difficult problems to deal with, and we kind of talked to the team, and we've decided to move forward with a totally different data set based on what those issues are, because it does need to perform well. I'm trying to stay a bit high level here, but depending on what your model's intended end use will be, these problems with your data can either be mitigated, or it can be project ending, or will require project swerving. And that's just something to keep in mind, that the direness of these data quality issues is going to depend on the project that you're working on, whatever the application, the end application may be, and things like that. So some other data quality dimensions are data integrity, data governance, security, encryption, and availability / access. I'm not planning on going in depth in these, but they are just other things or other dimensions that don't deal with the actual data set or whatever CSV file that you have. So when to assess data quality should be assessed before building the model and also after building the model. So before building the model, you want to look at your data set, see if there are any issues with it, if it needs to be cleaned up, if the issues can be mitigated at all, and what you should do about them. And then in terms of after the model has been built, when it's deployed, you're going to want to be looking at the test data set, but also kind of that new data, that population data that it is going to be deployed on. So what can we do about it? We've got data cleaning, a bunch of data cleaning techniques. So if your data is incomplete, you could, if the columns have too many missing values, you could consider removing the column totally. However too many missing values is, that is going to depend on the problem and what the data set looks like. So if there aren't that many, you might decide to just replace it with the mean or the max or some other type of data imputation technique. But with that and with all of these, it is helpful to have an SME who's familiar with that data or what that data might look like available to at least ask questions, especially if you're not totally familiar with what that application may be. If there aren't that many missing values, you could think about just deleting the relevant rows, or maybe that column isn't necessary for model building at all, so that might be okay. If the data is not accurate and consistent, you can see if you can either delete or correct those inaccuracies. Again, not always possible. It's going to depend on the data set. If there are duplicates, just remove the duplicates. If the data is not current, consider acquiring a more recent data set, or depending on your problem and application, you could at least make a note of final model assumptions. So if you have data, so for example, the Airbnb data set is from 2019. Is that going to be effective at predicting 2021 Airbnb prices? Probably not. A lot has changed since 2019, as we all know. Outliers, decide whether to keep or delete outliers. Again, that's going to depend on the subject matter. Bias, expand data set. So for that one example I was talking about before, maybe I could include images from other types of infrared sensors, try and expand the data set a bit. And then there are also a few other methods that you can do. Adversarial debiasing. Sometimes you can upsample on those on the training data. And then cursive dimensionality. I have a section on that below. And then feature selection and extraction. So the next portion is on bias variance trade-off. So bias is kind of the difference between the expected value of the estimator and the true value being estimated, and then variance is the variability of model prediction. So we've got this archery target here that shows the relationship between high and low values of bias and high and low values of variance. I think it's pretty straightforward. But we can also see that relationship over here. So if we have high variance and no bias, obviously these are kind of extreme examples. We have overfitting. If we have high bias and zero variance, we've got underfitting. And then I kind of think of it as like a tug of war where we want some type of balance between bias and variance so that we can fit well to our data. And the main con of having something that has high bias and or high variance is that it's not going to generalize well to new data, which for the most part is the goal of machine learning models. So we can move on. One example of that bias and variance trade-off is in this training versus test set error. We have model complexity on the x-axis, error on the y-axis, and as the model complexity increases, the error decreases on the training data set, but as it gets more and more complex and it starts to overfit on the training data set, there is this kind of V in the curve where it doesn't perform as well on the test data set. I realized I didn't talk about training and test data sets. Are you guys all familiar with the difference between training and test data sets? Awesome. Also got data transformations. That's going to depend on your model hypothesis space. And then here is dimensionality reduction, another topic that I find a little bit difficult to explain, but I'm going to do my best. So here we've got an equation with the formula for the Euclidean distance between any 2 points in Cartesian space. So each new dimension adds a non-negative term to this sum. So if you think moving from 2D to 3D to 4D, the distance between the points is not going to go down, it can only go up. And as that number of dimensions increases, the number of possible configurations of models also grows exponentially, and the number of configurations or combinations of inputs that is covered by the observations that you have in your data set decreases. So what that means is that as the number of features increases, classifier performance is on the y-axis, there again is this knee in the curve where your model kind of becomes fickle and fragile to new data. I think it's really easy to think about this in the context of like the KNN model, where if you have a lot of features, pretty much all of your points are equally far apart. So if you're looking for the k nearest points, it's not going to do a great job of classifying because they're just all far apart. So there are a few methods of dimensionality reduction. There are a few linear methods, a few nonlinear methods. Again, if you notice that a column really isn't adding anything to your model performance, you could just not include that feature, or you could combine a few features. But here are just a few techniques as well. And then the next two are cross-validation and bootstrapping. I do want to note that these methods can and are used with high-quality data as well. But reading some papers, I found that they can also be used when there is limited data when you have a limited data set. So k-fold cross-validation is going to split your data set into k configurations, and then within one fold, 1k of the data set will be used for cross-validation, and the rest of the data set will be used for training. So, and it kind of creates k folds, however many folds that you may have. So each data set is going to be used for validation at least once. And then another method is bootstrapping, where you sample the data with replacement. So it can be used to create an ensemble model. So if we have some data set, we can split it up with replacement into kind of, I guess, smaller data sets, create different models based on that. We have X different predictions, and then kind of aggregate those either by averaging or some other type of bagging method into one final prediction. And so this can kind of help upsample the points in your data set if you have limited data. Again, if you do, probably the first line of defense would be trying to get more quality data, but if you can't, these methods are there. I did now want to touch on technical debt a bit. So developing and deploying a machine learning algorithm, it can be cheap and quick. I don't think it should be. I think there are a lot of steps that you should take, like assessing your quality data and things like that. But maintaining is very difficult. They have their own technical debt characteristics. Again, this is another silent but deadly type of debt, and it can be very difficult to measure. So there are a few different sources, such as input entanglement. This kind of goes with data drift, so changing anything changes everything. If that distribution of inputs changes over time, that's going to, or it might affect the importance and weights of the remaining features. Correction cascade, so if you have model M1 trained on problem A, you have problem A prime, and you want to start from model M1, that resulting model M2 is going to be dependent on that first model. Data dependencies if you have unstable data, data that's changing over time, or legacy features, bundled features. If you've got this model that you've been building for a very long time and you're like slowly changing it and adjusting it and adding features without taking into the fact that maybe some of these added features make one of your legacy features should maybe be pulled down, maybe you don't need that anymore. Those are things to consider. Feedback loops, glue code, pipeline jungles, obsolete experimental code paths. I'm sure we're all familiar. Even if you haven't heard these terms before, I think it's pretty straightforward, and I'm sure most of us are at least a little bit guilty of this. It makes feature updates and innovations really costly when you're kind of trying to remember what you did and, oh, where does this variable used for again? It's really hard to mitigate technical debt. I think it really comes down to documentation, version control, again, kind of not working in a vacuum, but working together with other people and trying to keep track of things and making note of any assumptions that you're making, and so on. So that is technical debt. I have this great graphic here where we have, and it all came from this paper down here, everything that kind of goes into building a machine learning model, data collection, feature extraction, analysis tools, and so on. And you can see like the machine learning code is actually quite a small portion of that. So there's all of this background steps that really need to be taken, especially when assessing data quality, all of these other things. And then the actual machine learning code is actually not quite long or quite as big of a portion. A lot of it is verifying the data beforehand, verifying the data after, and all of these other things around. So I have some recommended reading at the bottom, but I think John is going to go into a hands-on example next.
Hi, I'm John Cilli. I work with Victoria, so I'll go into a little bit of example. So as Victoria touched on before, it's an Airbnb dataset from the website Kaggle. Just a good way to practice machine learning and other coding datasets and learn from other people's code that they post on the website. So it's a fun example. Everyone's familiar with Airbnb here, I'm guessing. If not, I can explain a little bit the concept, but essentially just hotels, but owned by just general people. So the agenda for my example, we're just going to do a quick introduction onto the problem scope, what we're actually looking at, kind of overview the data to get a better understanding of what the features are and like kind of what analysis we're trying to do. Then we're going to do examples. So I made like a baseline neural network. So disclaimer real quick, it's not going to be the best neural network out there. It's about data integrity more so and what it adds to the value and our prediction power. So it is only like 4 layers deep. So you can come at me if you want, but don't cut too deep into how many layers and what I'm actually doing with that. Then we're going to a bunch of examples of just tweaking small little things within how we manipulate our data and analyze it and see how much actually degrades our model. And in conclusion, like how much prediction power do we actually gain from good data integrity practices? Then is there anything that I missed, or what further things that can we do aside from what I talked about in this presentation? Can we further explore this data set? So quick into the problem scope right here. So we're just going to predict Airbnb prices. So that's going to be our target feature. And then our scope of our problem are Airbnbs in New York City in 2019. So if you scroll down a little bit. So as a quick overview, so we're just importing the data right here. So our target feature is price, and our predictor features are going to be possibly everything else. So our columns right here, ID, name, you can read through a bunch of them. I think most of them are pretty self-explanatory. But yeah, these are the features that we're going to be looking at. We'll filter through them later and stuff and kind of pick and choose which ones we actually want to look at. So first question we're going to ask, is our data set unique? So just go down a little bit. We look at the shape. So we have 48,895 rows by 16 features. We look at our unique values within our data frame for our ID, and it matches that, so that's good. We don't have any duplicated rows within our data set. So that checks out right there. We go into do our data types match what we're actually trying to describe. So we just do our data frame types. We have some objects, so those are going to be strings. So problem here is like if you have price and that's an object, we need to cast that as an integer or a float. Or let's say price is a float instead of an integer and it goes past 2 decimal places, and that would be a problem as well. But all these seem to match up right now, so we'll deal with categorical stuff later. Is it complete? So we're going to see is null and some of it. So we have some host IDs, some names and host names that are null, so we can just cast them to unknown as strings. Since they are just strings, they're going to be grouped out as categorical variables. And we do have last reviews and reviews per month that it's a large summer data, 10,000 rows that we have. So we'll go on to whether do we want to drop them, backfill, do we want to just take the max value of time since last review because they're probably new Airbnb data sets, or do we want to create a completely new frame that just says no reviews, that is going to be a new column that is just a Boolean feature. And we'll go down a little bit. We're going to look at the map. So this is latitude and longitude. It kind of looks like New York and stuff to an extent. You have Manhattan right here. Not great with the other boroughs. I know Manhattan at least. I think it's solid. So we keep scrolling down. So now we're just gonna group by like the boroughs and then like other types of variables and stuff. So the mean price, Manhattan's expensive. We all know that. Checks out. Brooklyn's somewhere in the middle right here, and then Staten Island and the Bronx are a little bit cheaper. Makes sense. No offense to anyone that's ever lived in those boroughs or does live in those boroughs. My one good friend's from Staten Island. I always make that joke towards him, but whatever it's called. Then we see that the county Airbnb, so Manhattan's the most, so that makes sense, and then Staten Island. The Bronx again, a little bit lower and stuff, with Brooklyn almost up there in Manhattan, which is a little bit surprising, but it seems to check out as far as I know. Talking to SMEs, as Victoria talked about, Forest Systems Matters experts, might give you a better understanding of, is this really a full representation of the population of our data set? Scroll down a little bit more.
And like most of the touristy stuff is in Manhattan, right?
Yeah.
So that would make sense.
Yeah. Then I don't know what you're doing in Brooklyn, but
Hipsters go there.
They have any recommendations on your visit, but then we kind of split it also by borough and then the type of room. So with Airbnbs, they split into 3 different types. They have an entire homeowner apartment, then you have like a private room, which is usually just like a little studio attached to a larger apartment. Then you have like a shared room. So most people usually, when you get an Airbnb, you want privacy, you want like your own space. So it does make sense that, well, this is mean price. We have countdown here, but the price will be higher for these. And then across the boroughs, the same trend as we saw above, held constant. And then the counts, yeah, you definitely don't see too many shared rooms. In my experience, I've never done a shared room and stuff like that, but I don't think it's I think you can charge too much for that. When you go down with this data, does make sense. And do we have outliers in our data? So like 2 big questions, we'll go more into outliers later and stuff, but like what actually constitutes an outlier and stuff. So like you can't just take like, 3 standard deviations outside the mean, take out all that data set, because there might be some meaning behind them. But the one big one that we did see within our data set is with price, the minimum is 0. I don't think people are just giving out free Airbnbs. That doesn't really make sense. So I can confidently remove that from the data. But if we scroll down a little bit more, we can see the max right here. But it's very apparent when you have a histogram. All our data is right here. But then we have like a few like penthouses in like New York City that are like way out here, like 10,000 and stuff. And like depends on the question you're trying to answer and stuff. Like maybe your customer does want to like actually like see very expensive Airbnbs, but like I didn't really want to take out the data because it is kind of meaningful to model some more expensive Airbnbs. But So without a SME expert, I don't think I was confident enough to take out the ones that are down here. If you go down, you can see like all our outliers are just in the thousands of dollars and probably like less than 1% of our data set. So that could be something that you can do with this model. We'll talk about later the end of ways to improve it. So these are the attributes of data integrity. So example 1 and 3, we'll talk about completeness. 5, consistency. And example 2, accuracy. Uniqueness, we'll talk about in example 4. Current data I'll touch on, but there's no specific example for that. Then outliers, example 2, and then feature selection and extraction for example 6. So this is how I just built my basic pipeline. Yeah, you can go down. So just importing all the packages I needed. Then this is my data manipulation function. So here we're going to drop ID, name, host name, last review, minimum nights, and number of views. So ID, that kind of makes sense because it's just one-to-one mapping of everything. Name is similar to that, same with host ID. There are some redundant hosts and stuff. Host name and host ID are very similar. And then as far as like reviews, when I was working with this model, minimum nights, it didn't seem to have too much correlation with actual prediction power. And then we have 3 categorical variables that we're trying to model off of. So we just did pandas.getDummies, which one-hot encodes these categorical variables, and it just returns the data set. And then here, this is just a simple way to do test train split built into the scikit-learn or TensorFlow dataset package. And this is a creator model, so it's in a sequential TensorFlow model. So our first layer just takes in the input dimension, activation functions Relu. Then we have 2 middle layers of just tanh, and then we have an output layer of just 1, since with 1 node, just because we're only predicting price, and we're using the atom optimizer with a learning rate of 0.001. Turns both those. Print dot is just to see if our model is running. It'll just print dots when for each epoch. This is plotting the history. So this is how we get our plots of our metrics and our loss functions. Keeps going down. And then this is our prediction data frame. So it's a large data frame of our predicted values versus our actual values. And then we can plot off of that as well. And our model accuracy at the end, we're going to do an absolute % error, and that just returns that. So within our baseline example, so we're going to do the data manipulation function that we talked about above, and then we're going to take away the 0 price and then drop the NA values. Going back to dropping the NA values might not be the best solution for this, but you can talk about other things like, I think a lot of the NA values are within the reviews. So we're going to take the max length of time since the last review that we see within our data set and then put that onto all of the NA values for that, because they're probably just new Airbnbs that don't have many reviews that are 0 reviews. So we go through this, just call our functions that we called before. We run 100 epochs and stuff. And then here, this is going to just be our loss function, our metrics, validation loss, validation metrics, and what epoch at each of those rows. There you can see this is our plot history. So this is mean absolute error, one of our metrics that we're trying to test on and stuff. Looks pretty smooth. Mean square, not as great as the other metrics, but it's not our loss function, so we don't care as much. And we go down to our loss function, which is mean absolute % error. And it's all right. It kind of like, our training goes down with time, but our validation kind of stays around and doesn't really improve too much after 20 to 30 epochs. Then we go down. Then this is our prediction versus, we're just going to use this for our charts below. But you can see to some scale, that's price and predicted price that you can see over there. So it kind of caps out as it gets very large and stuff. It doesn't map well for very large values. But anything around like the mean and median, it predicts decently well. So we get like a 60.5% accuracy for our model, and that's just absolute % error. Not the greatest, but also not the worst. It's just to show the trade-offs that you have of loss and prediction as we violate data integrity values. So here in this data set, we're just not going to remove any of the null values or drop any of the outliers. We're going to run through, and the big thing about this is kind of like just a fun example. It doesn't show any errors. So if this is a pipeline within other pipelines, it's literally just going to feed through without any error catching or any error handling. You will see when you scroll down, you'll see NA values and stuff. You will see empty plots. But the thing is that this is pipelined into another model that you're going to be working on. It will just feed that data straight into it because it still has this data frame right here. So if we scroll down to a more interesting example though. We can talk about what we want to do with NAs. I've touched about this before and during it. So do we want to remove them like we did right here? Do we want to backfill, front fill? If we sort them, do we want to use an estimated value based on other predictions? Do we want to create a new feature and a new value? So I talked about the new value of just taking the max number of days since last review and just input that into the NAs. Or do we want to create a new feature that's like no reviews, true or false and stuff. So those are two options you can also do. So this is taking the data with taking out the NAs and dropping them, but then now we're not removing the outlier of free Airbnbs. And it's the same workflow. You won't see any errors. Again, we'll have this data frame populated with non-NA and not a value numbers. But we'll see plots now too, and it looks to train decently well, like pretty similar. But then when we go down to our model accuracy and stuff, you'll see that's infinite, and that's because you can't divide by 0 and stuff. But again, this will still pipeline into any other models that you have linked to this neural network and stuff. And we can scroll down to what we want to do before we actually run this analysis. We kind of want to scroll up to, sorry.
More?
Yeah, just like what I did before early on the presentation, kind of look at just like the data frame described and kind of see like the distribution of the data. You might want a histogram. I think seeing the outlier of 0 is very apparent within a describe. But then if you want to see the outliers that are in the tens of thousands and stuff, a histogram might be a little bit better for that. We keep scrolling down. And then, like, how do we treat them? So it's safe to say that a price of 0 is safe to remove. But where do we draw the level again? Like, is it standard deviations outside the mean? Are we okay with losing, like, the very expensive Airbnbs? So I think a good way to, like, good place to start would be talking to a SME, a systems matter expert, that has more knowledge on actually what the customer wants and the actual data set at hand. And then we're going to go into completeness now. So here, I'm going to just remove 70% of Manhattan and then kind of see what happens here and stuff. So it's going to be a lot of redundant code again as we go down. And everything checks out, runs perfectly fine and stuff. But our accuracy drops around like 9% and stuff. Because when it's trying to predict the majority of the data that is in Manhattan, it's just completely removed and stuff. And a way to check this down below, the plot looks completely fine just because there's so many data points that we're looking at. But if we look at this bar chart right here, we say Manhattan's like the same size as Queens, which you don't need to be a SME to understand that. But in a more complex situation, you would want to have a more greater understanding of the problem at hand. Make sure that your data actually makes sense before just pipelining it into your model and just having it run, because Tensorflow doesn't understand any of these like high level like stuff. So I'm just trying to drive this point home like 100 times over. But
And would this kind of tie back to selection bias, where we're training a model that doesn't have a lot of Manhattan data, but when it's deployed, it probably would have a lot of?
Yeah, when you deploy into like an actual scenario and stuff, like say you take another data set for 2020 and stuff, then it's not going to really understand the concept of what Manhattan is within a statistical sense, as well as it should. And then now we're going to go into uniqueness. This is a little bit more interesting. So I just literally just copied 10,000 rows and just appended it to the data frame and ran it through. So if we scroll down, runs pretty well and stuff. Continue to go down. And then the big point here is our accuracy is like literally like probably like 0.5% to 1% from our baseline. But is this true like prediction accuracy? I would say no, because you're just having a lot of redundant data on the training and testing side. And neural networks do really well when it sees the same data twice. So even though it's like very close and you're not getting much prediction loss within here, it's it's just not actual real prediction loss. It's just predicting the same stuff multiple times and stuff. So it's a very inflated accuracy of the model. So the way to check this is just what I did before. Kind of look at the shape and look at the unique IDs and stuff, and you can see it's 10,000 off, and you can also see the duplicated number of rows is 10,000. So that's just a simple check you can do to check your integrity of your data. And then we're going to go into consistency. So here we just found another data set on Kaggle, and we just took it from Berlin, and we just pipelined it in, and it ran perfectly fine. So it's a different year in a different country and a different city, and it runs completely fine without any errors. As you see, it flows perfectly well. But we do lose 6% of accuracy. So it can train probably a little bit better on certain aspects, maybe like number of views or something that's transferable between countries. But then when you expand the number of neighborhoods out from like probably like 100 to now a few hundred, you're kind of touching on the curse of dimensionality and stuff. So if we scroll down a little bit to some of the notes at the bottom.
Whoa.
And also, now this is the plot. So you kind of lose the fidelity that you have with latitude and longitude, where you can see between block to block the price changes. But now latitude and longitude is probably modeling a completely different thing, where it's just modeling, okay, it's New York City and Berlin, more so than it's 16th Street versus 17th Street and stuff. So yeah, latitude and longitude have less effect, curse of dimensionality. Also a big thing, currency within these two. So with our New York City data set, we did know is US dollars. And Airbnb is I think is an American company. So we don't know if their data sets that they have are going to be in euros, like from Germany, or if they're going to pull out down the data and already do that transmutation itself. So that's something to check into. Then here's feature selection. So before I dropped a lot of these columns. In here, now we have a lot less. So we added a few of the review columns and a few others. And we're going to see how it trains. It's very sporadic and stuff. It doesn't train as well because it's trying to train on way too many parameters and stuff. And you do have about a 7% accuracy loss right here. Just way too many extraneous features, and it can definitely degrade the model. So how much prediction power do we actually gain from these practices and stuff? And how can we actually further improve these? So here I have a data set of all the accuracy of each of the models, and we have our plot below. So here, you do see this is the highest. This is the second highest, but again, it's seeing redundant data, so it is going to predict pretty well on that. If we go down, we can see the differences between the few of them. So we do gain, I don't know, for anywhere from like 5% all the way up to like 8.5%. This is infinite, so this bar goes on forever. But the uniqueness is a little bit lower, but again, on the topic of seeing the same data multiple times. So how do we further improve the integrity of data? We want to find probably more data, but then what happens when it's different cities and stuff? Like, would it be better probably maybe to find like Philly in New York? New York's a whole different animal than any other city probably in the world, but can we find different years? And what happens with different years besides just inflation? Because Airbnb is growing as a company itself, so the demand is increasing. How do you impact those factors too, instead of just accounting for inflation within your price? And then also the features that we have within this data set, we don't have like square footage when this was when the Airbnbs were built, and we don't have number of beds, number of bathrooms and stuff. So those are probably more correlated features within our data. Then the alternative ways to treat the null values and outliers, which I talked about before. Then this is just doing a quick correlation plot. As you can see, just doing a simple regression probably wouldn't really work really too well because none of these features are very well correlated with price and stuff. So, and that's about it. Any questions or any critiques and stuff? I'm open to critique 100%. Always willing to learn.
Not specifically this, John, but or maybe Victoria, you can answer too. Any thoughts on using TensorFlow versus Keras versus Pytorch when it comes to deep learning models?
Yeah, because they all do like very similar things, and I have practice within TensorFlow and stuff. This is like applying this to like choosing dashboarding like tools and stuff. Like it's whatever you're most familiar with, because there are going to be slight tweaks within like what you can actually do with their packages and stuff. But does anyone else have like experience with using different modeling tools and which packages have benefits for versus which?
So I use Pytorch. I think Pytorch I feel like is more customizable. So if you want to do something custom, you probably want to use that. Whereas if you want to do something a little bit more out of the box, TensorFlow is going to be a lot easier. That's my experience.
Yeah.
Also, when it comes to, maybe it's, maybe somebody else could answer this too. I don't know what's like at Picatinny, but do you all have some sort of architecture set up when it comes to clusters? We talk about GPU clusters for deep learning. Do you have anything like that set up?
Yeah, we do.
What do you
I don't know how old it is. It's called the AI Resource Infrastructure. It's not managed by anyone in our group. I don't know that much about it, but I only just learned about it maybe 2 months ago. So I just got an account set up and I'm going to start using it. But I know it does use GPU clusters. I don't know exactly how big it is. But again, like we're in that AI spring/summer. So I think a lot of that funding and resources is kind of going to like building up these resources for the workforce to use.
Did you use it for some of the previous image classification stuff?
It is being used for that one current one that I mentioned. Yeah, that defect classification. Yeah.
Are there any other topics or questions? So you can go. He can ask that question.
Maybe one subtlety in what you did is the loss. I think you used the absolute error.
I mean, absolute percent error, yeah, for the loss, yeah.
I think when you do the back propagation, like you take derivative of this,
Yeah.
it's just one.
True, because it doesn't count for the negative side of everything, yeah.
Well, so like if you do a mean squared error,
Yeah.
you actually like the weighting for each loss for each point becomes the difference between the truth and prediction.
Yeah.
And so it's going to weight the loss differently as well. So it might change these kinds of results.
Okay, cool. Thank you.
So I think kind of in conclusion, data quality, it can be a bit of a beast. I think there's a lot of, when there's problems with the data, the solution or the mitigation technique, it's not always straightforward. There can be subjectiveness involved, but I think having these discussions are important and collaboration as well when dealing with these data sets, I guess. I really enjoyed the discussion today also. So thanks for being an engaging audience.
Yeah, thank you.
Thank you guys. Thank you.